All right, good morning, everybody. Today we're going to do something mildly unusual, which is we're going to start chapter 5, but we're going to actually start in the middle of chapter 5 and do the second part first. So today we're going to talk about the derivative form of the momentum principle, which we introduced last time in the context of talking about an analytical solution for the motion of a mass on a spring. And we're going to use it in a context that allows us to actually, in the end, the goal is to deduce unknown forces. To deduce unknown forces, we are going to have to know the rate of change of momentum. So we're going to be reasoning backwards, essentially, from the rate of change of momentum, a known rate of change of momentum, to an unknown force. And so that's the game we're going to be playing for the next week or so. So let's review where we came from and then get started. The reading assignment reflects this. So the reading assignment for the first part of the reading assignment for chapter 5 introduces a couple of concepts and then goes to talking about curving motion. And we want to talk about curving motion first, partly because it's just a lot more interesting than things not moving or moving in a straight line at constant speed. And also because you're going to need to apply some of the concepts we covered today in next week's lab. The big picture here is determining force from motion. I really can. Determining, I can spell force from motion. And that's kind of backwards from what we've been doing now. Previously, we knew a force and we were predicting a final momentum. So we were always doing something like P final is P initial plus F net delta T. But now we're going to use the momentum principle in a different way. So we're going to write it in its instantaneous form as a derivative. The instantaneous rate of change of momentum is equal to the net force acting on a system. And the idea is that if we know this, then we can find this or deduce contributions to it. Now, you've actually already done this in a very simple situation, because we've reasoned that if something, an object or system, is at rest and remains at rest, then the net force acting on it is zero. And so we have to think about all the forces we know are acting on it, add them up, and make them come out to zero. And that is a form of reasoning about this, because if something is at rest and remains at rest, we know that the momentum is not changing, since it's 0 and 0 and 0 and 0 and 0, right? Now, a really important piece of this equation is the vector equality piece of it. So vector equality, and let me remind you, it's something you might not have thought about for a while, but if a vector A is equal to a vector B, or a vector dp dt is equal to a vector f net, that means that the magnitude of these vectors is the same. And it also means their directions are the same. So if two vectors are equal, their directions have to be equal. So the vector A hat, the unit vector in the direction of A, is the same as the unit vector in the direction of B. And that's going to be really important. So applied to the momentum principle in this instantaneous form, if we know the magnitude of the rate of change of momentum, we know the magnitude of the net force acting on an object. If we know the direction of the rate of change of momentum, we know the direction of the net force acting on an object. And what we're shooting for is to be able to actually know the rate of change of momentum of something, which we can deduce from its motion, and therefore deduce F net. So there are two parts of what we're going to do today, and they're both important. So the first thing we're going to do is talk about a really systematic way of counting interactions, counting forces. And that's important because it keeps us, and we can often identify that there are interactions even if we don't know their values. So example, we know there's a friction force on something because it's slowing down even if we don't know its value and have to calculate it. And the second part is going to be finding dp dt from what we know about motion. So this is basically the right-hand side of this equation. That's the F net piece, and this is the left-hand side. This is the dp dt piece. Now, we're going to be really compulsive about a systematic approach to this because it allows us to avoid a lot of traps that are easy to fall into. It allows us to avoid double counting forces. It allows us to avoid missing forces. It allows us to keep from introducing spurious forces that aren't really there. So here's one, counting forces. So the first part, the first step, there's several steps. So this first step is explicitly choose a system. And write it down and stick to it. So everything else is the surroundings. The second part is to identify every object in the surroundings interacting at a distance. And we know of two kinds of distance interactions. There can be gravitational interactions or electric interactions. And the key part of this sentence is actually object. Our system interacts with objects, and so we have to have an object that's the source of this interaction. If you can't name an object, it's probably not a real force. The third part is to identify every object in the surroundings that touches our system. Okay, so the key part of here is, again, object. Got to count, and touching. So, and then we're done. Even if there are other objects in the surroundings, as long as they're not exerting a force at a distance and they're not touching our system, we're done. So stop and draw a force diagram. That just records this information and helps us reason from it. So let's take an example. Let's see if I can, there we go. So here's an example. We have, you hold a yo-yo from the string. So here's your hand. Here's a string. And here is a yo-yo. Now, let's just go through this. Let's just go through this as if we were going to solve for the tension in the string or something like this. So the system is the yo-yo, and that's the object that's experiencing the forces. Objects interacting with the yo-yo at a distance. Well, gravitational forces, there's certainly an object exerting a gravitational force. It's the Earth. So that's a gravitational force. There's some other things exerting gravitational forces, the sun, the moon, Mars. Okay, but these are small, so we can neglect these for now. And that's it. There's nothing else interacting with our system at a distance that's significant. What things are touching our system? Well, the string. Another thing touching our system is the air. And the air actually does interact a little bit. There's a little bit of buoyancy due to the fact that the air is a little bit denser below the yo-yo than it is on the top. But not that. It's not a very big effect, so we can ignore it. But notice what's not in this list. The hand. Because the hand doesn't touch the yo-yo, and it exerts a negligible gravitational force on it. So it's not part of this. It's not, we don't count it as exerting a force. So if we drew a force diagram, we almost always just represent our system by a dot. We would draw two forces. There's a force downward. It's a gravitational force, and we'll put the name of the object here to make sure we really have an object associated with the force. We have an upward force due to the string, and we'll call it a tension force. And that's it. So now we can do our analysis. We could solve for the tension force, for example, by saying, starting with the momentum principle, dp dt equals F net. We know that the rate of change of momentum is 0 because this is just hanging there. So it's at rest. So F net is 0. And F net is composed of a sum of the gravitational force plus the tension force. And so we deduce that the tension force is equal to minus the gravitational force, which is going to be a 0, plus m times g 0. So that's a simple example of how this worked. Now notice the key point though is we didn't choose the hand as part of the system. Now we could have chosen a different system here. We could have chosen the same physical set of objects, but we could have chosen the system as the yo-yo plus the string. So it's okay to have more than one object together. It's a compound object in the system. So in that case, the objects in the surroundings interacting at a distance are still the Earth. But now the things touching are the hand and the air. So our system will still represent by a dot, even though it doesn't look like a dot because it's got that string. But now the forces acting on it are a little bit different. This is still the gravitational force exerted by the Earth, which is a little bit larger because we're considering the mass of the string. And this is now the force by the hand. So the hand is pulling up. And now we could actually solve this for the force that the hand has to exert. Notice that this previous analysis where our system was the yo-yo didn't tell us anything about the force the hand was exerting. But if we include the string as part of our system, then the hand is touching the system. And so so we still have dp dt of our system is F net, and that's F gravitation plus F hand. 0 equals 0. So that is Fg plus Fh. So that we can solve for the force by the hand, which is going to be minus F gravitation, which is actually 0. Here we have the mass of the yo-yo plus the mass of the string, 0. Okay, so that's a really simple example, but it gives you the idea of what we're doing. A third example here is that is from something you did in lab a week ago. So you had the Earth and a spacecraft. And at the end of lab, you actually started the spacecraft with a velocity in that direction, and the spacecraft actually made an elliptical orbit around the Earth. Why did it do that? Well, looking ahead a little bit, we can take the same approach. So here's our system. If we choose the system as the spacecraft, the surroundings in our model, the only thing that was there was the Earth. We didn't have anything else interacting with it. What was touching the spacecraft was nothing, because it's in space. And we can draw our free body diagram here, or sometimes this force diagram is called a free body diagram. You'll hear people talk about that. And we know that the Earth exerts a force, it pulls on the spacecraft here. So we know that the force by the Earth is in that direction. And now if we apply the momentum principle, it's more interesting because we have dp dt equals F net, but the momentum of the spacecraft is absolutely not constant here. In fact, if we look a little bit later, we're going to find it going that way. And when it gets here, it's going to be going that way. And in fact, it's going to be, I don't know if you noticed when looking at this, but it's actually going faster. And so dp dt is not 0. And so it's a much more interesting situation. In fact, from this vector relationship, we know that dp dt is not 0 and it's numerically equal to the net force acting on it. We know the direction of the net force because we put it in the model, that's the Earth. So it must be the case that the direction of dp dt at this instant is actually perpendicular to the momentum. So when the path is curving, dp dt is not 0. And that's the case we want to explore today. Now, there's a simple way to, in this case, we happen to know the net force. But in many cases, we're actually going to be working from the rate of change of momentum to find a net force. So we want to be able to go both ways. So how would we find dp dt? Well, the scheme is this. We're going to take a snapshot of the system here. So here's the path. And we want to find the rate of change of momentum when the spacecraft is right here at this instant. So dp dt, the direction of dp dt is actually going to be the direction of delta p for a very small delta t. So it's the direction of delta p over delta t, which is a positive constant for a very small delta t. And we can find that graphically. So what we need to do is we need to draw the momentum of this spacecraft a short time before it gets to this point. So I'm going to exaggerate the distance here just so I can draw it, but we really want kind of a small, so P initial here, tangent to our curve is in this direction before it gets to this point. And so this is the time delta t before it gets there. We want to take the same time interval after it gets there. And we'll draw the momentum of the spacecraft there. So this is an interval delta t, and that's an interval delta t, or really the same interval. And then we can get a delta p, and we can imagine sliding those two, making those time intervals smaller and smaller and smaller, sliding those two vectors closer and closer together until we get a limit and we get the instantaneous value. So let's see what this gives us. We'll just redraw these vectors to get, so we can subtract them. So here's our initial momentum. There's our final momentum. And so delta p is final minus initial. So we start at the tip of p initial. We draw a vector to p final, that's delta p. And so we find that the direction of dp dt is, in fact, in this instant, perpendicular to the momentum of the spacecraft. Here is a question. So we have an object moving along this trajectory outlined by the black line. So the object is moving whoops, moving along this line. And we look at its momentum at the one instant, p initial, and its momentum is always tangent to the path, of course. So and at this instant, we find it tangent to the path over here, p final, and a little bit bigger. And so the question is, which of these arrows correctly represents the delta p, the change in momentum from initial to final here? Okay, so most of you are completely correct. Delta p is p final minus p initial. And so arrow 3 here is indeed the correct answer. And if we take this, redraw the trajectory, and then draw dp dt on the graph at the moment halfway between these two things, we'd see that the rate of change of momentum of this moving object is in the direction of delta p, that it's turning and the magnitude is getting bigger. If you said 1, you probably weren't paying attention, but in fact, what is 1? What is vector 1? What does this arrow represent? That's the change in position, isn't it? Yep, that's exactly what it is. Change in position, not change in momentum. So different vectors are different. So let's think about what makes an object's trajectory curve, about the forces necessary to make an object's trajectory curve. We notice in up here in our example of the spacecraft that that at the instant we're talking about, the force is actually perpendicular to the momentum, and that's actually kind of suggestive. So what I'd like to do is show you a video. And what's in this video? In this video, one person rolls a bowling ball on the floor, and the other person runs around, so gets it going, and the other person runs around hitting with a hammer trying to make it go into a circle. And I want you to watch the video and think about the direction in which the person who's hitting it is applying forces. Okay, so here goes. Okay. So let's think about the directions of the forces that were applied here. So in the video we had yes, that person is indeed terrible at golf. However, if he wasn't actually trying, I mean, golf with a bowling ball is actually an interesting idea anyway. But I want you to think about what the direction of the forces applied. Think about the direction of each blow that was that was struck here. Whereas he hitting the ball in the direction that it was already going, was he hitting it in the direction that he wanted it to go in the next second? Was he hitting it perpendicular to the momentum toward the center? Was he hitting it perpendicular to the momentum away from the center? So let's see what you said. And the majority say correctly that what he was doing was he was hitting it at every time, which is why he had to keep walking in a circle. He was hitting it perpendicular to its current momentum, directed toward the center of the circle to make it go in a circle. And that's actually a pretty important result. So let's go back and watch it again. Notice that he really is hitting it toward the center of the circle. He's not hitting it in the direction he wants to go. He's not hitting it away from the center of the circle. And then when he stops hitting it, it goes in a straight line. So that's a key feature. So it looks like in order to get something to go in a circle, to get something to curve, you need to, so in curving motion, you need a force perpendicular to the momentum to get something to turn. Now, if the magnitude of the momentum is not changing, which was true in this case, the ball's speed was really not changing very much. It was only its direction changing. Then that could be F net. But more generally, both can change, as you saw in an elliptical orbit. And so it's pretty clear that you're never going to make something go in a curve by applying a force either in the direction it's going or exactly opposite to the direction it's going. So applying a force parallel to the momentum is definitely not going to make it curve. And so that'll make it speed up or slow down, but it's certainly not going to make it curve. So to make it curve, you need some piece of a force that's actually perpendicular to the momentum. That's supposed to be perpendicular right here. The geometry symbol. So remember high school geometry here. So in general, we saw last time when we talked about friction forces that we could express a force as the sum of two vectors, two perpendicular vectors. So we talked about the force on the table by the block, on the block by the table. And if the block is moving that way, then the table exerts a force that way, but it was convenient for us to express it as two different forces, the sum of a force that way, which we called a normal force, and the sum of a force opposite to the pulling force, which we called a friction force. So F table was the normal force plus the friction force. So in all cases, we can write in the momentum principle, if we have dp dt equals f net, we can write this as f net perpendicular to what? To the momentum, plus f, a component of f net that's parallel to the momentum. And that suggests correctly that we could also write dp dt, the rate of change of momentum, as a sum of two things. A piece that's perpendicular to the momentum, and a piece that's parallel to the current momentum at this instant. Now remember that momentum and rate of change of momentum can be in very different directions. So we saw with the spacecraft example that when the spacecraft was here with momentum there, we found that dp dt was actually in that direction. So these two things, that's the rate of change of a quantity and the quantity, are not the same thing. And not very surprisingly, we can, because of the property of direction having to be equal in a vector equality, we can actually then break down the momentum principle into two pieces. So we can see dp dt, the component that's perpendicular to the momentum, is equal to the component of the net force that's perpendicular to the momentum. And the component of dp dt that's parallel to p is equal to the component of the force that's parallel to momentum. And by parallel, I mean parallel or anti-parallel along the same line. Okay, so how do we find these components? So how to find say f net, a piece of f that's parallel to momentum, and a piece of f net that's perpendicular to the momentum. And I'm just going to write parallel and perpendicular here, but recall that what we mean is perpendicular to the momentum of the system. Well, mathematically, we can use a way of combining vectors called a vector dot product. So and it's a way of combining two vectors that actually gives you a scalar. And that scalar actually ends up with information about the angle between the vectors. So this is a new vector operation that we haven't talked about before. And it's an easy thing to do. So if we have two vectors A and B, we write this as with a dot in the middle, like a multiplication symbol. And what this is actually a sum. So we take the x component of A and multiply it by the x component of B to get a scalar. And then we take the y component of A and multiply it by the y component of B to get a scalar, and the z component of A times the z component of B to get a scalar. And so we get this scalar. So for example, if we had a vector 1, 2, 3, if that's our vector A, and we take the dot product with a vector -4, 5, -6, we would get the sum 1 times -4 plus 2 times 5 plus 3 times -6, which is equal to a -4 plus 10 plus a -18, which gives us a -12, if I can do arithmetic correctly. Okay, so that's not hard to do. The question is, where did the geometry information come from? So let's consider a couple of situations. Let's consider two unit vectors, A hat and B hat. And let's take their dot product. So A hat dot B hat is equal to 1, 0, 0 dot 1, 0, 0, which is equal to 1. Well, okay, what if they were in different directions? So let's make A hat go that way and B hat go that way. So now the dot product of A dot B is 1, 0, 0 times 0, 1, 0, which is equal to 1 times 0 plus 0 times 1 plus 0 times 0, which is equal to 0. So if they're perpendicular to each other, it looks like it comes out to 0. Okay, what about if we had a unit vector A and a unit vector B in those directions? So we'd have A dot B is equal to 1, 0, 0 dot -1, 0, 0. So we get -1 plus 0 is equal to -1. And Cole, we'll get to that in a minute. But it's a good question. So notice that we have here a function that seems to go from 1 to 0 to -1. And if we kept going, we'd have A hat, B hat. That's going to be 0 again. So this sure looks like we've got a cosine function hiding in here. Okay, so it's oscillating between 1 and 0 here. And so in fact, the cosine of the angle is actually in here. And so we can actually come up with another form of we can actually extend the ways to evaluate this vector dot product. So it's certainly equal to A sub x, B sub x, plus A sub y, B sub y, plus AZ, BZ. And that's equal to the magnitude of A. In the case of our unit vectors, that was 1, times the magnitude of B, also 1, times the cosine of the angle theta between the vectors, where this angle is theta, and theta is less than or equal to 180 degrees. So it's the smaller angle. Indeed, there is a VPython command for a dot product to make your lives simple. So if we typed dot A comma B, that would give us the dot product of vectors A and vectors B, which you had to define before, but that gives you the dot product. Cross does indeed do the same thing for a cross product, which we haven't talked about yet. We will get there. We talk about angular momentum and torque. So let's do an example. Suppose we have suppose we have momentum of an object in a direction like that, and we apply a force on the object in a direction like that. We want to find the component of F that's perpendicular to P and the component of F that's parallel to P. Well, F dot P hat, the unit vector in the direction of P, is going to give us the magnitude of F times 1 times the cosine of the angle theta between F and P. And so that's going to give us the parallel component. Because remember, when two vectors were parallel, the angle between them was 1, and we got 1. So that's F parallel. And then just to get F perpendicular, we just take F minus F parallel to get F perpendicular. So let's try it and see what we get. Let's say that the vector F is -2 to 0, and the vector P is 3, -1, 0. So we need P hat. So the magnitude of P is just the square root of 3 squared plus 1 squared, which is equal to the square root of 10, which is 3.162. And so P hat is going to be P over the magnitude of P, and that's going to be 0.949 negative 0.3160. So F dot P hat, which gets the magnitude of P out by taking the unit vector in the direction of P, we're getting the magnitude of P out of here, and we're just worrying about components of F, is going to be equal to -2 times 0.949 plus 2 times minus 0.316 plus 0 times 0, and that equals a -2.530. So F parallel is equal to this times P hat. So it's equal to F dot P hat, that gives us the magnitude of F parallel, times P hat, which gives us the direction of F parallel. So it's -2.530 times our unit vector 0.949 negative 0.3160, which is equal to -2.4 0.80 newtons. So that's F parallel, and we could draw it here on our diagram. I mean, if on our diagram as So it's negative x, positive y. That makes sense. So this is going to be the component of f parallel to p. Notice that, again, parallel just means along that line. In this case, it's actually acting opposite to the momentum. And now to get f perpendicular, it's just f minus f parallel, so that's negative 2 to 0 minus negative 2.4, 0.8, 0 newtons. And that's equal to so that's going to be equal to negative 0. It's equal to positive 0.4 because it's minus. So 0.4, 1.20 newtons. And so it's both plus x. And so that would be the component of f perpendicular to the momentum. Well, in this case, so the question is, why don't we just take the unit vector of f to find something parallel to it? And we would if we wanted to find something parallel to the force. But our goal here was to find the force component parallel to momentum and the force component perpendicular to momentum, because that actually tells us, allows us to predict what's going to happen to the momentum in this next little time delta t. Because the parallel component of the perpendicular component of f is not 0, that means that the momentum will turn. Okay, so that tells us that the momentum is going to, in the next little time, momentum will be rotated counterclockwise. And the parallel component tells us that the magnitude is going to decrease, actually. So we would draw a new momentum, which would be something a little bit flatter and a little bit shorter. So in this case, we wanted the magnitude of f to be in this. If we just want some vector that's parallel to p, we could. Okay. So how did we know how to multiply f? And it wasn't exactly f we multiplied by hat p, was it? So when we take, so let's back up, because that's a good question. So how did we, where did this step come from? Okay, when we take the dot product of the force with a unit vector in the direction of p, so here's our, here's the unit vector p hat, okay? We get a scalar, and so this is the magnitude of f parallel. Okay, so what we got is so that's f cosine theta. That gave us the magnitude of this vector here, magnitude of f parallel. But we need to turn it into a vector, so we need to multiply by the unit vector in the direction of p to get the actual vector parallel force. Because remember, what was it parallel to? Well, it was parallel to p, so we want to convert it back to a vector. Does that make sense? And then once we've got it as a vector, we can subtract it from f and get f perpendicular. Again, what unit vectors are good for is taking magnitudes and giving them directions. which equation, Vic? You'd say, shouldn't there be a vector sign over the last f, but which? So this is important. So let's try it. Let's think about it another way. So let's redraw our diagram here. We can still, so here's, I don't really need axes actually. So here is our momentum. Let's make it. And here is the force that we're applying on the object at this instant. Okay, and we can see that this force is not exactly perpendicular to P, and it's not exactly parallel to the momentum either, right? In fact, it's got a piece that's perpendicular. It's a sum of two things, one thing that's perpendicular and one thing that's parallel. So qualitatively, graphically, what we want to do is this. We want to express this vector f as the sum of two perpendicular vectors, one that's perpendicular to P and another one that's parallel to P. And it's going to turn out to be a very important thing to do this, because this perpendicular piece is the piece that makes the momentum turn, and this parallel piece is the one that changes the magnitude of the momentum. So that's what we're trying to do. Well, the question is, so that's our goal. So then we can write F equals F perpendicular plus F parallel. Okay, and we know that this one turns the momentum, but it doesn't change its magnitude. So what it really does is it changes P hat. And then there's this one changes the magnitude of momentum, but doesn't change P hat. Okay, so they have different jobs. The job of the parallel component is just to turn the momentum. The job of the perpendicular component is to turn the momentum. The job of the parallel component is to make it larger or smaller. So we need these things as vectors. Now, so when we take if we took the dot product F dot P, that would give us the magnitude of F times the magnitude of P times the cosine of the angle theta between them, and this angle theta is that angle. But we don't want the magnitude of P in here, because we're trying to find something that contributes to F. Okay, so this is undesirable. So instead we take F dot, a unit vector in the direction of P hat. This gives us the magnitude of F cosine of theta, which in fact is F cosine theta actually is equal to the magnitude of F cosine of the magnitude of that is equal to cosine theta, right? So that's what we want. But now we've got a scalar. So this is a scalar. It's the magnitude of F parallel. And a scalar doesn't do us any good. We can't subtract what we, if we want to find F perpendicular, then we need this F parallel as a vector, right? So, but we need F parallel as a vector. Well, we already know the direction. That was, the direction was p hat. So if we multiply this F dot p, which is a scalar, times p hat, then we get F parallel. Well, so Seth says, would it be possible to take the magnitude of F and multiply it by sine theta and cosine theta? No. You want it to multiply it by cosine theta. I mean, this is, so you want the magnitude of F times cosine theta to give you the magnitude of this, but it's still, you're still stuck with a scalar. So you still need to multiply by a unit vector in the direction of momentum to get it in the right direction. And then, yeah, and if you know the angle, that's a legitimate way to do it. But in a lot of cases, especially, so you need to be able to do both of these things. I mean, if you take F cosine theta, remember that that actually is a way of evaluating the dot product. That's actually mathematically, so this piece actually is F cosine theta. And so, no, that's already taken care of. So should you multiply it by minus p hat? No, because what you got is the projection of this vector F onto the line of P. You already took into account the fact that the angle theta is bigger than 90 degrees. And the way you know that is that you actually got a negative number here. So so we already took into account that whole angle theta thing by taking the dot product. Okay, and it came out negative, which means that the angle is greater than 90 degrees. So that already accounted for the angle. So we need to just multiply by p hat. Okay, so the next piece of what we want to do is actually think about parallel and perpendicular components of momentum, of force parallel and perpendicular components of forces and of dp dt in cases where things are going around in curves. And what we're going to do is think about something moving in a circle. Now, not all curves are circles. I mean, we want to be able to analyze motion that looks like that, okay? So things don't always move in circles. You saw just from playing with orbits a week ago that an elliptical orbit is a much more common thing than a circular orbit. So we want to be able to analyze motion with arbitrary curvature. But if we analyze motion with a circle, then we actually have something we can apply to arbitrary curves, because even if something is traveling in a strangely curvy path like this, it turns out that at any instant there's some circle that's tangent to the path here. So instantaneously, if it's here going that way, it's as if it was traveling in that circle. Sometimes the circle might actually have a larger radius of curvature than the path here. So this is called, oddly enough, the kissing circle because it just kisses the path. And so at any instant, we can analyze curving motion by thinking that it's instantaneously moving in a circle with a particular radius of curvature. So therefore, analyzing motion in a circle actually tells us something that's going to be generally useful. So our goal here is to show you that for motion in a circle at constant speed, which is a special case, well, actually just a circle. Motion in a circle, we're going to find out that we can actually at some instant find the rate of change of the direction of momentum, and that's going to be the speed at which the thing is traveling over the radius of the circle. Now, where did this rate of change of direction of momentum thing comes from? Well, this is just calculus. dp dt is a time derivative of momentum, and we know that we can write momentum as the product of the magnitude of the momentum times the unit vector in the direction of momentum, right? And so we're differentiating a product. And by using the product rule, this product has two pieces. So we apply the product rule. And we get the first piece is the rate of change of the magnitude of momentum times p hat, plus the magnitude of the momentum times the rate of change of p hat. Well, that's interesting because this is the vector piece, and this is a scalar because it's the rate of change of a scalar. So this is the piece in the direction of p hat. And so this is the piece of dp dt that's actually parallel or anti-parallel to the momentum. And we see here that what's changing here is the magnitude of the momentum, change in the magnitude of the momentum. So this is, we would call dp dt parallel, the parallel piece of dp dt. Because we can write dp dt as the sum of two vectors that are parallel and perpendicular to p, just like we did with f. This piece is a scalar times the rate of change of a vector, which is itself is a vector. This is the rate of change of a vector. And this piece is the change in direction. So without affecting the magnitude. So this is the piece that's to change in direction is perpendicular to the vector. So this is perpendicular to P. So this is the component of dt, b dt perpendicular. Now, mostly we'll actually just, we'll mostly just write those symbols, but this is what they're equal to. And in some of the homework problems, you'll find these formulations here. So you should note that that'll show up in homework when you're asked for some of these things. And so we haven't quite gotten to a proof, and we have 2 minutes to do it, which isn't enough. So what I'll do is show you the results and we'll go over the proof next time. So the goal, the result is that if we end up with the rate of change of the direction of momentum equal to the speed divided by the radius of motion, that means that the perpendicular component of dp dt is equal to the magnitude of p times the speed over the radius of curvature, and that's equal to gamma mv times v over r, or gamma mv squared over r. And if something is moving slowly with respect to the speed of light, so we have dp dt perpendicular, and this is a magnitude, is equal to mv squared over the radius of curvature.